So my name is Andrew Margenot. I'm a soil scientist at the U of I here in Urbana-Champaign. If it's dim in here, it's because it is because the eclipse is happening real time outside my window. It's a little dark. So I'm here because I'm really glad to be able to share some of the work that my group at U of I is doing on what I think is an overlooked source of non-point source nutrient losses. Meaning, when we think about nutrient losses, specifically nitrogen and really phosphorus in this example, we think about point sources like wastewater treatment plants, and we think of non-point source. And on the latter, we tend to think of non-point source as being the same as agricultural losses. And what you're about to hear is a compilation of evidence and ongoing work that points out that's not quite true. As a matter of fact, the non-point source sector includes ag, to be sure, and ag is certainly a major contributor within the non-point source. But there's also non-agricultural non-point sources. And a specific one that I'll focus on today, because there are several, is streambank erosion, meaning when the banks of streams, creeks, and rivers slough off, they load phosphorus and sediments into waterways. And because we've not really gotten good data on that, we have been incorrectly pinning a lot of our phosphorus losses on agriculture when a good chunk of them are probably not from agriculture. And I'm saying probably because we don't yet have great data for Illinois and for the greater Midwest. So that's the goal of today's 30-minute talk. So let's begin with some context. We all live, well, most of us who are hearing this, we mostly live in the MRB, the Upper Mississippi River Basin, specifically the Upper MRB. And as we can see here, it's largely cropland, pasture, and then in red, cities. If we think about nutrient losses, I'm sure you've heard that we need to decrease nitrogen losses and phosphorus loads by a certain amount by a certain date down the road. Well, the way that we think about this, meaning researchers, landowners, and managers, the EPA, is by really two nutrients. We tend to think of nitrogen losses, specifically nitrates. It's the major form that we lose, and then total phosphorus losses, typically phosphate. So we often see an image like the one on the left, not great pixelation, but it's often found on the internet. On the right-hand side is a more clear picture. Nitrogen losses on top and phosphorus on the bottom. Darker colors means more losses. So let's zoom in on phosphorus because the focus of today's webinar is phosphorus losses from the non-point source sector that are not from agriculture, but we have thought incorrectly that they are. So if we think about how much phosphorus are we losing in the MRB, 31 states, on average, it's 0.7 pound of P per acre. This is not P2O5, this is elemental P. So roughly we're talking like 2.5 pounds of P2O5 per acre. Not very much in terms of an agronomic magnitude, but it is significant for water quality. And now if we hone in on the upper MRB, where much of Illinois is situated, the average here is almost double of the entire MRB. It's 1.2 pounds of P per acre. Now, our state contributes from 10 to 16%. That number will vary by year and based upon the estimates, but we are the #1 loser of phosphorus of all of the 31 states that drain into the Mississippi River and thus the Gulf of Mexico. Illinois leads this, all these states. Not a great thing to lead. So of course, there's a lot of research and practices being done by farmers to mitigate these losses. Now, I want to step back and think about what I mentioned earlier. Agronomically, these are not huge losses, right? A couple pounds of P2O5 per acre, given that we may have applications of 200 pounds of DAP per acre, that's on the order of 92 pounds of P2O5. Let's think about the concept of PU sufficiency or PUE. So PUE is when you understand how much P is going into your system and how much is coming out with grain harvest. And you want a higher PUE. That means that you're being more efficient and likely more profitable with your inputs of phosphorus. Now, if we think about PUE across the union, we find that the upper MRB is actually pretty efficient. And Illinois is a leader in the efficiency of our phosphorus fertilizer usage. We are from 60 to 80, in some counties in central and north state are upwards of 80% PU sufficiency. For context, global PUE across all global croplands is 16%. So we're going almost 4 times higher than the global average in our efficient use of phosphorus. Now, this might seem like a paradox, right? How is it that Illinois is one of the most efficient in the union and definitely in the world with our pea fertilizer, and yet we're the #1 loser of phosphorus to the Gulf of Mexico? It seems like a contradiction, but it's not. Really, the way that you can reconcile this apparent contradiction is it's a difference in magnitudes. What matters for water quality doesn't matter as much for agronomy in terms of just a significant amount. So here's a similar figure. You're kind of getting the gist here. We're #1 for P losses. And now it's shown by the Huck 8, simply a designation of watershed. So you're seeing all the different watersheds of the MRB. And to be a hotspot, these darker colored watersheds, you're losing around 200 kilos of P per kilometer. To translate that from USGS's map, that's about 1.8 pounds of P per acre. Now, if we think of a typical application of DAP as 200 pounds of DAP per acre, that's roughly 41 pounds of P, not elemental, sorry, that is elemental, not P2O5. Now, why does this matter? Well, 1.8 pounds of P per acre is less than 5% of the application that a typical acre might be getting in DAP every 2 years for corn soybean rotation. Now, this is important because it means that if we achieve 95 PUE, 95%, excuse me, we're incredibly efficient. That's probably unlikely. Even then, 95% PU sufficiency of our input still leaves room for losing that 5% that would still constitute a hotspot of P losses. So to put it differently, this is a really tricky problem because few things are 95% use efficient. The gasoline that turns the wheels in your car, 30% use efficiency of turning wheels. The rest is lost as heat energy, for example. Same with nuclear power plants, etc. So this then is the disparity that explains why we're still very efficient. Our state of Illinois is a leader in PU sufficiency of fertilizer and still losing phosphorus. Now, the assumption that we're making here, which I'll argue is incorrect, is that we're losing the fertilizer that we're not using. And that's not quite right. Now let's think about the basis for that. I want to talk a little bit about how non-point source loads are calculated. So we've got point sources, things where there's a pipe and you can measure it. These are permitted and they're regulated for their P emissions. Think of a wastewater treatment plant or a factory. And then you've got the non-point sources, which are everything else that you can't measure. So by definition, you cannot directly measure the non-point source. So how do we come up with these estimates of what's coming phosphorus loss-wise from non-point source versus point source? Well, we have gauges, these things called super gauges that are on the mouth of the rivers that hit the Mississippi, that drain the state of Illinois. We can do some math based upon the acreage, etc. We get a decent, good estimate of how much total phosphorus leaves the state. And by law, point sources in Illinois have to keep records on what they emit. So if we subtract the point source losses from the total state losses, by difference, we calculate, but we don't measure, we calculate non-point sources of phosphorus. Why does this matter? Well, we make the mistake, including in the Illinois Nutrient Loss Reduction Strategy, the NLRS, that non-point source is synonymous, it's the same thing as agricultural losses. And here's a snapshot on the right from the latest biannual report of the NLRS, where in green we've got agricultural losses of P, but that's wrong. That's non-point source. And the reason why this matters is that we need to cut up the green slice of that pie chart into ag non-point source and non-ag non-point source. And that last one is very challenging. A dominant source of non-point P that's not from agriculture is this. This is an example of a stream bank, a really tall one. It's really almost like a bluff that's sloughing off by the action of the creek that's in the foreground. And this is a pretty tall bluff. We're talking about 25, almost 30 feet tall. There's a lot of phosphorus naturally occurring in our soils. And as I'll show shortly, most of our phosphorus in stream banks is not from fertilizer. And even if you farm on the stream bank, it's still largely not from fertilizer because of the high native fertility, phosphorus-wise, of our soils in this state. So a bit of background on stream bank erosion. So first thing to know is that stream banks meander. What does that mean? It just means that, like a snake, they slither back and forth across a flat landscape. Water tries to find the low point. You spill it on your kitchen table, you'll see where there's a bit of a slant because it'll go that way. And if we have especially flat landscapes, like in especially central and north, but also south Illinois, relatively speaking, right? This is not Colorado with the Rocky Mountains. Then there's no clear winner of where the low point is, so there's even more meandering. And as that stream meanders, like the Margenot shown in the top right figure, it'll slough off the banks. This then is an entry of sediment from what was a streambank soil into the waterway. And so we're losing a lot of phosphorus, largely from native or naturally occurring phosphorus in our loess-derived soils. Loess is the parent material from which soils of our state were born. It's very high in phosphorus, good thing for farming, not a great thing for streambank erosion and P losses. Now, there's another complexity, not a complication, but a complexity here, which is that when we erode a streambank soil, a very small fraction of the phosphorus in the stream soil will immediately become soluble and be measurable as dissolved reactive phosphorus, called DRP. It's a common metric that USGS measures that we care about for water quality because it directly drives algal blooms. And most of the P, as we've shown in this example here from Cole County, south of Champaign County, is that, most of the P in our soils, and thus these stream banks, is not solubilizable right away. There's phosphorus bound to carbon as organic matter that has to be broken down by microbes. There's phosphorus bound to iron, to calcium, and these have varying release rates. They will dissolve into DRP at timescales that might take up to years, if not decades. So there's a gift that keeps on giving of chronic leak or chronic release of phosphorus from these sediments once they're eroded into the stream channel. Now, why does this matter? Well, we know, for example, from this past November of 2023, the biannual NLRS report for Illinois found a 35% increase in P losses as a 5-year average, driven by the non-point source sector. And a lot of fingers got pointed towards agriculture, specifically that farmers are over-applying phosphorus, and this is why we're losing so much phosphorus from the non-point source sector. Except farmers have not been over-applying phosphorus. In fact, farmers in Illinois have been under-applying phosphorus since 1990. Where am I getting this number from? There's a great paper here by Mark David. Through 2000, they charted the amount of phosphorus as a balance, what's going into the state as fertilizer, what's going out of the state as export of crops. And we recently extended their calculation to 2020, and we find the same results, that on average, as a state, we are removing more phosphorus from croplands with grain harvest than what we're putting on as fertilizer. So farmers are not over-applying. In fact, they're under-applying, and yet we see a 35% increase in phosphorus losses. Well, this could be explained by the legacy of these sediments that are still giving off phosphorus years or decades after. So this is important because it shows you how understanding streambank erosion not only refines what we call source attribution, where is the P coming from farmland, from streams, from factories. It also helps explain why we see these largely unexplainable increases year to year in phosphorus losses, even though farmers are not over-applying. Again, they're under-applying phosphorus, and they're doing BMPs on the landscape. So we sought to understand for Illinois, what does streambank erosion contribute? And we began global, of course, big picture first. And what we found here was that globally, if we look at all the studies anywhere in the world, the amount of sediment and phosphorus, and they're linked because sediments carry the phosphorus, the amount of sediment and phosphorus in a watershed being lost is on average 40% from streambank erosion for sediment and 31% for phosphorus. And this matches this last number exactly with the state-specific estimate, conservative, meaning that it's likely underestimated, for Iowa that came out 2 years ago, meaning 31% of our phosphorus as a global average, and for the state of Iowa, is coming from bank erosion, which means that we've been counting that incorrectly, 31% of phosphorus losses from agriculture in the non-point source sector. So ag is still contributing 69%, if I'm doing my math correctly. It's still appreciable, it's still the dominant source, but 31% is not nothing. Now, we honed in on a second study and looked at just the published articles done by scientists across the MRB, shown here with the red dot. And as you can make out, there's a lot of studies that have been done in Iowa, Missouri, up into Minnesota, but our neck of the woods, Illinois, and then the further part of the eastern Corn Belt into Pennsylvania even, there's largely an absence of studies. And there's only 51 studies total ever done in the MRB. Of these, most are short-term, less than 15 years, which is important because, as you saw from a few slides back, we get the meandering of streams like we saw for the Margenot at decadal timescales. You need a deep vision or a deep time perspective here. Now, if we look at the values that we found, overall, the amount of phosphorus that erodes from stream banks, the figure on the right-hand side, from these studies can range as low as 2% to as high as 44%, the figure up here, this green dot that I'm touching with the cursor. Now, that's a relative contribution of the total watershed export. In terms of hard numbers or absolute values, this is equivalent across these studies to 0.7 pounds of P per acre. Now, remember, that is exactly what the MRB average P loss is across all sources, non-point and point source. Now, this can't be true. It can't be true that streambank erosion accounts for every bit of phosphorus that we're losing. We know that just not to be real because point sources are losing. But what this says is that of the studies that were conducted largely in the Western Corn Belt, in those systems, the magnitude is on average the same as the MRB-wide P loss. So again, this is definitely, meaning streambank erosion, an appreciable source of P losses. Let's talk more at the state scale. So those are specific watershed studies. What about states? So if we think about what states have a number, Iowa has a number, roughly, meaning at least 31% of your total state. That includes point and non-point. So it'd be more like 39% if you account for the non-point sector only of P losses is from streambank erosion. Across all the other MRB states, which overlap with the Corn Belt, no idea. There's not a single published metric of a statewide estimate. To confirm this, we looked through the different state nutrient loss reduction plans or strategies, and we looked at them from all of the states that have one. There's 13 states of the 31 that have one. These are the states that are the biggest losers. And what we found was that there's not really any mention of streambank erosion in most of these. We then checked out the updates to the state plan. So the state plans were made roughly 2012, 2014, in response to the federal EPA telling the MRB states, you guys need to get it together and figure out how will you tackle this challenge. States have risen to that challenge to make up these plans, and then they make updates to these plans, depending on the states, every 2 to 4 years. Our state does it every 2 years. And what we synthesized in this published paper was that in Illinois, we do actually the best job of all the states, I would argue, of at least recognizing that streambank erosion is occurring, but we don't really have any numbers on it. And some states don't even say the word bank or streambank erosion. They're totally unaccounting for this process, for their P loads. Now, as we argue in this piece with colleagues from Iowa State, FFAR, and other policy groups, overall across the MRB, we're not quantifying P loads from bank erosion. And that means that they're absent from our strategies at the state level across the MRB. Now, there's 4 consequences from not quantifying P loads from bank erosion. One is that we're overestimating ag contributions of phosphorus losses. Second is that we're losing a chance to maybe manage a source of non-point P losses. Things like streambank shielding or doing wetland construction to buffer the sediment loads. And because of number 2, we might be misdirecting resources. Finally, and I think this is really critical, and it's part of my job as a public servant at the U of I, to talk to the public and the policymakers to communicate to them that our expectations on decreasing P loads from Illinois may not be accurate time-wise because of these legacy sediments that take a long time to move through the river systems. There could be P losses that we see for the next 30 years, even if we stopped all agricultural P losses tomorrow. So that's an example. It's a bit exaggerated, but it gives you a feel for, we have to grapple with the fact that the timelines of drawdown of P losses might be decadal to even centennial in some cases. So you might ask two questions here. First is, hold on, why is this not quantified? If it's so important, how have we missed this? And why aren't people working on Streambank erosion loads? Well, the simple answer is it's really hard to do. It's not a trivial thing to get good data. And especially, again, you need decadal timescales to quantify this. So if we look at our Illinois Plan on Nutrient Losses, the NLRS, we have a pretty, I think, well honest explanation, which I admire because it's straight with us. And it says we don't include stream bed and bank erosion because we don't have the data. That's pretty honest. So what we're doing right now in my group, along with our colleagues at U of I, is trying to fill this gap. We're in year 2 of a 5-year project supported by Illinois NREC dollars that farmers and fertilizer suppliers are paying into. We're coming up with that number to inform accurate policy and just assessments. So for this, we're quantifying bank erosion through different means. One is the traditional erosion pins. This is what we have used for decades, where we can look at the amount of pin exposed as the bank recedes as it erodes. And the rate of exposure of rebar length horizontally installed is a proxy of bank erosion. We also can do finer scale quantification of stream banks with lasers, and then aerial lasers, LiDAR, which the state conducts every decade or so. And finally, we can use remote sensing by aerial images going back to 1930. For example, my home has an image of it. It's actually an empty lot in 1930. And in the same way, as most parts of the state have aerial images from pre-1940, we can reconstruct the bank meandering to estimate erosion. So to give you a flavor of what we're doing, we're looking at 9 Huck 8s. These are the major units that we tend to think about for watershed size. And these are across the major landscape types of Illinois, which are called MLRAs. Basically, we've got something on the order of 300 plus different stream sites. Each one has multiple dozens of bank erosion pins, as well as the remote sensing approaches going back to 1930. And what we found is that most of these banks are receding about 10 millimeters per month. That's about, what, 2 inches or so? My math is not great here. Sorry, 0.3 inches, 0.4 inches. And there's a lot of phosphorus, though, that's entailed in that. But there are some stream banks, as we can see here, that are eroding a lot more, up to 100 millimeters. That's 10 centimeters. So that would be about 4 inches per month. Now, this is to give you a flavor of what we're doing with the historical imagery, aerial. We can see here in yellow, 1938, and in red, the contemporary bank position. So we can estimate when the bank shifted with the stream shift, how much sediment was loaded in this phosphorus. So that's the first question of why is there not data, and what we're doing to fix that with Illinois NREC support. So the second question that you might be asking is, all right, that's fine, but I might question, someone has told me, why are you calling this non-ag, non-point source? Could ag indirectly be impacting stream bank erosion? And the culprit that's often proposed here is tile drainage. The idea is that because we've tiled these landscapes, there's more flashiness. So first, I'll explain about flashiness. It means that when it rains, the streams surge more quickly and with more power soon after, because the tiles are a conduit for rainwater to exit the system and hit the stream. And the answer is that depends. So there's a recent study as of a few months ago, back in December, that shows across the Corn Belt, they looked at the 3 I states. If you measure flashiness, where on the y-axis here, a bigger number means more flashiness. If you split watersheds into low infiltration soils on the left and those that infiltrate more strongly or a higher rate on the right, as we get more tiling in the watershed, left to right, we decrease flashiness with more tiling. So tiling helps mitigate stream flashiness, which should decrease bank erosion. And in some cases, meaning in soils that already infiltrate well, we have the opposite trend, where tiling more leads to more flashiness and thus more bank erosion. This is important for 2 reasons. One is that it means that we can't just say that tiling and how we manage water in agriculture always exacerbates bank erosion. It's not that simple, it depends. Second, it points to, in some watersheds, we can actually tile to decrease this issue. The third implication, there's a third, I guess, is that we don't really think of tile drainage in intentional way necessarily for watershed scale aspects. And there's, I think, a lot of room here to think about how do we plan watersheds in a way that can mitigate, in these examples on the right-hand side, effects on bank erosion. So in reality, there's multiple factors that together conspire to impact, and with funding from national corn growers, we're doing another study, another meta-analysis to understand what this is globally speaking. And as a quick update, here's what you're seeing, here's what we found to date. Most studies on tile drainage have been done in, well, the origins of tile drainage. It really began in South Scandinavia and North Baltic Sea Basin, Germany, Poland. In fact, indentured servants were recruited from Germany and Sweden and brought to Illinois specifically because they knew how to tile. And that's how we got tile in Illinois, was because of their expertise. So not surprising that we see this distribution. So I want to now talk a little bit about another term that is relevant here, and that would be residual phosphorus. So I've talked about streambank erosion causing legacy phosphorus, which is, as we define in this paper, the phosphorus that was lost in the past, whether or not it's from fertilizer, or as we saw from banks, it's not. And it's still in the system hydrologically, and it's still causing losses today. A second related concept is residual phosphorus, sometimes mistermed legacy P. And this is simply phosphorus that was put on as a fertilizer or as manure in the past. It was not removed with crop harvest, so it's still there. The important point is that it is not contemporary P losses. So the way that we get at the amount of residual phosphorus, what we're trying to do now for Illinois to quantify it, is by a mass balance. The idea is that we know what's going in as an input, we know the outputs, and by difference, we can calculate the residuality. A positive balance, so inputs are more than the outputs. So there's more going in than what's coming out, a positive balance, that is residual phosphorus. Now let's think about this at the state scale. Here's that graph again that I want to really drill down into. The estimate of how much of a positive balance was put down as fertilizer in Illinois is shown by the green area. So again, farmers have not been over applying, they've been under applying since 1990 to present day, but there was a period where from 1960 roughly to 1990, there was net over application and accumulation shown in green. And overall, this amounts to roughly 4.9 billion pounds of P, not P2O5. That would be more like 10 billion pounds of P2O5. On an average, that's roughly 200 pounds of P per acre, if you divide that number by the crop acres. Now, that seems like a big number, but we have so much phosphorus in our soils. Specifically, we estimate 95 billion pounds of P to 3-foot depth, that this accumulation of 4.9 billion pounds of P is only 5% of what's already there. Now, if that enrichment of 5% is in the surface, where it's liable to be lost by runoff, that can still present a problem. And here we get back into the legacy P concept. Here's a different example of how this could happen, especially with U of I recommendations pre-1990. This is the Mara plots. As you probably know, they're at the U of I campus. Established in 1876, the second oldest continuous ag experiment in the world. And here it is all synchronized, all the rotations in the corn phase. And you can make out from the chlorosis, some of these plots sure need some fertilizer. Now, to illustrate the residual phosphorus and the legacy effects of that, we looked at phosphorus balances because we have records going back to 1876 and really with high certainty 1888. And what we can make out here is that we have a lot of P buildup in just 15 years. So on the graph on the right, we've got 2 of our 24 treatments at the Mara plots. Orange is unfertilized and blue is fertilized. And so unfertilized, meaning we're cropping corn on corn every year, nothing added. We still get 25 bushel corn somehow. And then we've got in blue the fertilized. First it was with rock phosphate, then manure, and then DAP. And we can see in phase 2 with rock phosphate, the U of I recommendations were as high as 2,000 pounds of phosphate rock per acre every couple of years. And we see a massive increase in the positive balance, meaning we built up phosphorus. And today, the majority of our net residual phosphorus in 2020 was largely put there in less than 20 years, 100 years ago. So this phosphorus is still going to stick around for quite a long time. Here's why this matters. Some great work by Lowell Gentry at a Douglas County site with Dan Schaefer, shown here. where they found that where there used to be swine barns, shown here on the left-hand panel, there is very high soil surface Bray phosphorus. So we're talking Bray levels of 300 pounds per acre, so 150 ppm at the maximum. And these are over these tiles, and up to 44% of the phosphate lost as DRP through tiles today is explained by the high buildup of phosphorus in these soils from the swine production from pre-1950. So this is the idea that past phosphorus buildup, not contemporary applications, can still be driving the losses that we see today. Why does this matter? Well, I'll end on this example here from the Baltic Sea Basin. The Baltic Sea Basin is the biggest hypoxic zone in the world, not the Gulf of Mexico, and it's gotten worse over time, from 1906 on the left to 2012 on the right. And they did a study where they tried to look at different sources of phosphorus hitting the Baltic Sea Basin. And to break it down, they looked at 4 sources. In green here would be background, what they also include as streambank erosion. And like any background over the past decades, the past 100 years, it's not going to change. It's just always going to happen. And then they've got legacy phosphorus in the mobile form, meaning the DRP that we just saw from Lowell Gentry's study in Douglas County. So we've got buildup of manure or fertilizer P that's still leaking DRP today. And it peaks in 1980, then begins drawdown by 2000 with BMPs like drawdown based on soil tests. Then we've got direct coastal effluent in orange. That means discharge of sewage and industrial waste into the sea itself. It peaked in 1980 and fell by a factor of 5x, so 80% reduction in point sources in the Baltic Sea Basin by 2000. Good example of how point sources can meet and help support P loss reductions. But so too with the agricultural sector, which is defined as rapid transport in this paper. In blue, it peaked in 1980, and with BMPs, like reduced tillage, the proper application rates, they also decreased it by almost 4x. So what is that, 75% reduction? This is I think, a great success story. The non-point source, or specifically though, agriculture in blue and point source in orange, have decreased their P losses by more than 4-fold. And then the authors went on to say, well, what if we increase P use efficiency, as people often argue is a solution for ag reducing P losses? And remember again, we can have 95% PUE, the opening slides, and that still leaves room for severe water quality loads. And not surprisingly, even if the Baltic Sea Basin states or countries like Germany, Finland, achieve what we already are doing in Illinois at 80% PUE, there's a marginal decrease in total P loads because the majority of it is still coming from the background of bank erosion and the legacy phosphorus of residual P in soils. So this illustrates that we need to quantify both streambank erosion as well as its sister concept or pool of phosphorus known as residual phosphorus in soils. Okay, so to summarize all this, I know we're a little bit over time. Non-point P losses are agronomically pretty minor in magnitude, but they are important for water quality, and that's the apparent paradox of P in Illinois. They're also largely erosion driven, be it from fields or from stream banks. So to me, this is more of a conservation challenge. Things like cover crops and conservation tillage help reduce our P losses. And as we know, farmers in Illinois are not over applying phosphorus. They're not. We have the data for the past 30 years. Third point here about non-point P losses is that right now we don't account for stream bank erosion, so we're incorrectly pinning some of our P losses on ag when that's not in fact true. This then leads to the importance of quantifying legacy phosphorus, both in soils, what we should be calling the residual phosphorus, and also in sediments already entrained in our riverine systems across the state. And that's important because they can mute or diminish the immediacy of BMP effects on P loads. It might take us 20, 30 years to see BMPs on ag fields translate to DRP losses because of the high background from these sediments and this residual phosphorus in soils. So we have to quantify, as our lab is doing at the U of I with the support of funders shown here and farmers across the state. We're trying to quantify this question: how much and how long do we have these lags in water quality because of stream bank erosion? We need to quantify this to accurately apportion ag versus non-ag contributions, maybe manage a non-point source of phosphorus through stream banks and hydrology of the watershed, better use our resources for NLRS targets, and I think really importantly, communicate to the public and policymakers who I think largely misperceive the complexity of the problem. I'll end on this proposition. I would argue that phosphorus loss reductions are more complicated and harder to achieve than for nitrogen because of these lag times. So with that, thank you for your time. Happy to answer any questions by email or if you're on this phone call or on this webinar, excuse me, right now. Thank you.